Let's start the discussion on subsurface scattering by comparing this to diffuse reflection. If we look at diffuse reflection, what you'll notice is that the same general phenomenon is happening in the real world. Light enters into a medium, it bounces around, and exits at different angles. That's what makes diffuse-looking objects diffuse. And the same thing happens with subsurface scattering. However, the main difference is how far the light is able to propagate into the medium. So let's take a look at this example. We have light, it's hitting a tomato. We can see that light propagating through the medium. And then as I turn on this light with my shirt, which is a diffused object, we no longer see that light spreading out. And so if you're ever wondering whether or not an object has diffuse reflection primarily or is more subsurface, you can bring it through this experiment and that'll tell you really quickly which it is. As you can imagine, there's a few different ways of describing this scattering within computer graphics. The first way here is single scattering. And single scattering, it just takes one bounce within the medium. In other words, light goes in the medium, it meets with a sample that's sent from the camera, and then from there, the information is collected and sent to the render engine so that it knows how to shade that particular pixel. Now, this area right here is considered the subsurface distance. That's how far light rays are able to enter into the medium. And we also have this setting called the scattering phase. Now, the scattering phase is designed to say, is the scatter more likely to bounce back towards the light source, or is it more likely to bounce through the object? So, what you have to ask yourself is light more likely to scatter away from the object or through it? Now, if it's going through the object, then that means the scattering phase is equal to 1. If it's scattering more away once it leaves, then the scattering phase is -1. And by default, if you want a little bit of both, then you have a value of 0. What you'll notice about single scattering is that it's really fast to render with it, but it's also not very accurate. So if this is a purely diffuse material right here, if I now turn subsurface on by saying 1, the render engine's going to automatically bring down the diffuse weight. Now we have a full subsurface weight. Here I have single scattering selected, and this distance is at 0.1 meters. As you can see, a few things happen by doing that. For one, we have areas like the whiskers and the rim along the eye that went dark. And the reason why they're dark is because those particular areas have a depth that is less than 0.1. So when our subsurface distance is greater than the depth of that particular zone, then we get this strange artifact where things begin to look dark. So I'll just give you practical advice of when to use single scattering and when not to. Single scattering is great when you have something like a slab of marble as a good example. The subsurface distance isn't very large. It could be something like 0.001. We still want that bit of a glowy effect to it. And, well, let's actually go maybe 0.005, something like that. We still get some of this subsurface effect, and at the same time, we don't have to really kill our render times, and it's nice. So if you have a situation like that, the depth isn't very far, and you can just define a scattering phase, and you're good to go. That's great. However, if you're ever dealing with, let's say, skin, or let's say some sort of plant material that is more complex and thick, then what you can do is change this to full subsurface scattering, and it's going to use a different algorithm to calculate a more accurate version. But as we'll find, full subsurface scattering, even though it generally looks better, is a lot more difficult to render. And so let's talk about that process and what's happening there. With single scattering, we needed to make a direct connection from where the camera was sampling to where the light was coming from. And so this needed to happen. However, with multiple scattering, what can happen is this. A light ray can start like that, as an example. If this was single scattering, it would have never reached to where the camera is trying to sample from. But because it can bounce around in the medium, this light source has now found its way to where the camera is sampling. And this more accurately represents what happens in the real world. Now, the problem is all of these bounces take a lot more computation, and that's why the renders go a lot more slowly. But the result is generally more realistic, and it's generally better because this is simulating all these different bounces. So one thing that multiple scattering will do for you versus single scattering is it'll improve the quality of the shadows and specifically how subsurface scattering illuminates the shadows. So if we look in areas like this, with single scattering, we wouldn't see this nice soft illumination in a shadow area like that. And that's really one of the biggest differences between a multi-scatter versus single scatter in a visual sense. So the best thing to do with this is if you have the time to render this, then go ahead and use multiple scattering because it's going to give you a great looking result. But otherwise, if you want just something really quickly and you just want a little bit of that subsurface effect, then single scattering is a great way to go. We also have another SSS mode here, and that's this random walk for Karma. This uses a different algorithm, and it's pretty cool. It renders out really quickly as well. And I don't really know the specifics on it as much. I think this is a newer thing that Side Effects is developing. But if this gives you great results, then go for that as well. So there you go. That's the basics of subsurface scattering. I want to switch gears here and go back to transparency for a second. I want to talk about this transmission color and this at distance color. It's kind of similar to the idea of subsurface scattering because as light travels through a medium, what's going to happen is that even though it's glass, it's still going to bump into atoms along the way, so to speak, and some of that energy is going to be turned into heat. Now, we know that once energy is lost, that allows for colors to appear. So as a ray travels further and further through a transparent medium, what can happen is that light begins turning into a specific color. Well, that's what's being described with this transmission. So if we, let's say, choose a red color like that, and a distance, let's say the distance is really shallow, 0.001, then we can begin dialing in how exactly light goes through that medium, or how it gets colored as it travels through the transparent medium. Now, what this at distance is referring to is it's asking you, okay, at what distance will the light become this color, this pure red? So the higher we go, the slower light is going to change into this color. If we have an at distance at 10, as you can see, the light begins turning into a different color, but it doesn't do so very quickly. We now have these red colors beginning to show up, and it's beginning to change the color of the glass as light travels through, but it's never reaching this full red. And that's actually a very common thing to do whenever you have a transmission setting. You take it to a color that's pushed really far, and then you use this at distance to dial in how much of that effect you want. So for glass turns green as it, propagates through. And it's a very slight effect, so we don't need a value of 10. We can do maybe double that, 20, probably about 20 or so. And this behaves like glass that we're used to seeing. So anyway, I just want to bring up this transmission color and at distance. It's kind of similar to subsurface scattering in the real world because it's hitting these atoms and it's losing energy every single time light is being transmitted through that medium.